All right, I think enough, complete. So we can go on. And so you hear me fine, yeah? Like, all right, that's good. All right. Yeah, as I told you, like normally, as the true economist, you know, like with very high aspirations, we don't care about R squared that much. However, here in this particular, for this particular task, it's actually like a very good indicator. It means that we can predict the mileage of our car number 75, yeah, the one that's not in this sample, can predict it quite well. So we can explain 65% of the variation. It's a good thing for this task. So now we can refer to the bottom panel, and in the bottom panel things are more interesting. Sorry. First of all, we have this coefficient. Yeah, so like on the left part, it shows you the dependent variable. So for us, it's MPG. And we know the weight. It's the explanatory variable. The coefficient is minus 0.006, yeah, some number. And this is our beta hat. Yeah, like from the theory, remember this is our estimated beta. We don't know the true beta. Yeah, like only God of statistics knows the true beta. We can only try to estimate it, basically to guess it. Yeah, and with more or less confidence. So sometimes we are more, sometimes we are less confident. And here we have a set of additional indicators, and all of them are kind of important. First of all, when we run the regression, we test the null hypothesis. Yeah, so like maybe you can put it down somewhere, because that's kind of an important fact. It's very basic. Maybe you know already, but nevertheless, it doesn't make it less important. Normally, when we run this regression, we test the null hypothesis. Yeah. So we have a null hypothesis. So like null from nil, from zero, which tells us that the coefficient, this beta hat, is not statistically different from zero. Yeah, this is what the null hypothesis is. So null hypothesis means that our coefficient is equal to zero, so we have no relationship between, in this case, weight and MPG. So this is always the null, which we test. And if we reject the null hypothesis, then we could say, all right, there is relationship. And this is relationship we cannot kind of ignore. And then if we reject the nil or the null hypothesis, we take the alternative hypothesis, which says that beta hat, oh, no, the hypothesis is about beta. Yeah, beta hat is the stuff that we use to analyze the true beta, yeah, but like the hypothesis we make about true betas. So the alternative hypothesis H1, sometimes it's put, is that coefficient is not equal to 0. So that beta is not equal to 0. Yeah, so we just have a very simple task. We have to find we have to analyze this coefficient if it's equal or not equal to 0. And then the question comes, how do we do this? Yeah, like, is it 0 or not? Yeah, like, if you come to the shop with this amount of money, it's quite likely that this is something like close to 0. Yeah, like so it's less than 1%. Yeah, like it's very little. So maybe it's 0. But at the same time, it's not 0 exactly. So how do we analyze it? And we analyze it by running some tests. First thing we are interested in is the standard error. So standard error tells you how precise we are when we measure this coefficient. So basically you remember the regression equation was MPG equal to beta 0, this is the constant, plus x, which is weight here, times beta 1. Yeah, this is our regression equation. So to calculate beta 1, we can just divide MPG by weight. And we basically do this for every observation. And then we can see how often, for this average coefficient, is similar to individual coefficients. So let me show you what I mean. So we can write AV plot, and it shows us the graphic representation of our regression. Yes, it's the same cloud of data with regression line fitted in. So I only have to. Oh, all right. Yeah, now it is. So we see that, for example, in this case, yeah, where I point, or in this case, our estimate is very, very precise. Yeah, like these points lie on the line completely. However, in some cases, we're slightly off this line. However, it's still a nice approximation. Yeah, so like these points are slightly off the line. It doesn't make the line less valid. Yeah, because we cannot predict everything. Of course, some cars consume less fuel. Some cars consume more fuel just because of some characteristics of this car, which are not weight. Yeah, so this is completely normal. Some cars are better with the engine, some are worse, and many, many, many factors that we can think of. So we see that standard error here is you can see how much smaller it is compared to the coefficient. Basically, what we want to have, ideally, to find something meaningful, we have standard error that would be smaller than the coefficient, and the kind of substantially smaller than the coefficient. And here we see that our standard error is 11.5 times smaller than the coefficient. So it means that our estimate is quite precise here. So it's like coefficient plus minus bit less than 10%, which is a good good approximation. So we've just generated t-statistics, just divided coefficient by standard error. And this t-statistics we normally use for reference to analyze if its coefficient is big compared to standard error or not. So this is what we care about. Because if standard error is high enough, then we could say that like it's too much of variation in these coefficients. So this relationship doesn't hold universally. It doesn't hold for everything. We have to be sure that it doesn't. So we cannot be sure that it holds for everybody. That's what it is. And there are special statistical tables. Oh, they're called like t-distribution tables. And there you'll see like for how many observations, for how confident you want to be, you'll see the threshold levels of t, of this t. And then you can know how certain you are if you reject the null. And normally, these statistics have to be bigger than roughly 2 by module. Yes, like if it's minus 11, plus 11, it doesn't matter. The value of this thing, so like the module of this number, has to be bigger than 2. This is a rule of thumb. Of course, in the tables, you will see it's sometimes it's a bit smaller. It depends on the number of observations, number of variables, and so on. But you can say that here we have some kind of space, so we're quite confident in this. And then we come to the fourth column. So this is the p-value. In this statistical table, you will see that the p-value is the level of confidence with which you can reject the null hypothesis. Yeah, so this is another weird formulation. So in statistics, people don't say if something is right or wrong, but people would say that this shows the probability. You can also note it down because this is a very weird formulation, but if you read it for a while, it makes sense, it starts making sense. Basically, it tells you the p-value, what's the probability of you making a mistake by rejecting the null hypothesis. Yeah, so it tells you in what share of cases you are wrong if you don't believe in null hypothesis. And here we see that this is very, very low. Basically telling you that if you don't believe in null hypothesis, and you remember null hypothesis means there is no relationship. So if you don't believe in null hypothesis, so if you say that there is something between these two variables, you are wrong with this probability. Almost with 0 probability. It's never 0. So we cannot be 100% certain. So if you extend it, at some point you'll see the number. But here we're like 99.9% sure that we are not wrong by rejecting the null. Yeah, now things are become easier. We cannot say we are right. Yeah, like in statistics, you don't say you're right, but you're not wrong, which is like for normal person, it's the same, but not for a statistician. All right. So now we know that we can be quite sure that we can reject the null hypothesis, meaning that like we expect that coefficient, even though it's small, it's not equal to 0. And that's a good thing. We found something meaningful. And then if it happens, we can say that this is statistically significant. Yeah, so this is called statistical significance. And normally we have 3 levels of statistical significance. Because like here it's 0, it's quite easy to believe. But what if we have something we're not as sure, but we still want to make some inferences? And normally in econometrics, you have 3 levels, 3 kind of threshold levels of confidence. So this is the 10% level, or sometimes people call it 10%, sometimes people call it 90% level of confidence. So I think the correct version is 90% confidence, meaning that everything that has p-value, if this thing is bigger than that, the coefficient is officially not significant. So if the probability of making mistake is more than 10%, we cannot reject the nil. We say no if this is, imagine if this 0.1 would be here, we would say already, no, this is not statistically significant. We cannot be sure that there is a statistically significant relationship. If we are between 0.1 and 0.05, we say that this is coefficient, it's not strongly significant, it's weakly significant. Yeah, so there is some connection, but we don't believe it to be very strong. However, we already can suspect something. So, and then in this sense, we say that the coefficient is statistically significant at the 90% level of confidence. If p-value is below 0.5, no, 0.05, 0.05, it's important. 0.5 means not significant at all. If it's below 0.05, we can say that, all right, in this case, so it's between these two values, between 0.1 and 0.05. We say that this coefficient is statistically significant at the 10% level. At the 90% level. If it's between 0.05 and 0.01, we say it's significant at the 90% level. And if it's smaller than 1%, we say it's significant at the 99% level. We cannot be sure for 100%, it never happens. Sometimes in medicine, people have confidence levels of 99.99, so like they have very precise estimates. However, it's never 100%. So here, in our case, we could say that this is definitely significant at the 99% level. So it's very strongly significant. All right. And the last thing that we have in this table is confidence interval. And the confidence interval tells us, so before, like, with basically these columns, we made sure that our coefficient is not equal to 0. With 95% confidence, we are evaluating how precise we are about the size of the coefficient. Yeah, so, and we can say that we are 95% confident that the true beta lies within this interval. So we are 95% confident that the true beta lies between these two numbers. And for example, you see that 0 is not here. Yeah, both are negative. So 0 is somewhere on the right. And these numbers are quite far away from 0, relatively, of course. We're 95% confident that 0 is not there. And we see that this number falls exactly between these two. So how do we get confidence intervals? We normally take coefficient and subtract and add to it standard error multiplied by some special coefficient which you can find in the statistical table, which basically is determined by the level of confidence. So here we have 95% level of confidence. You could have 90% confidence, you could have 99% confidence interval, and then of course the constant would differ. If you have a higher level of confidence, higher than 95, you have to expand your confidence interval. Yeah, then it will be a larger interval, because the more numbers you include in the interval, the more certain, the more confident you can be that the true number is there. So for example, if you need the 100% confidence interval, you say minus infinity plus infinity, because all numbers are there, and we're 100% sure that the beta will be in this interval. However, maybe it doesn't give you much information, because it just tells you that yes, beta is a number, some number. So there is some trade-off. And here, for example, you say like, I'm 90%, 95% sure that our true beta lies between these two numbers. For example, it might be this coefficient. I believe this is this coefficient. If not, it's something close, something within this range. If you want to be very precise, so like if you want to come close to this, narrow the boundaries, of course you become less confident. Yeah, because the more certain you are, the less, the smaller the interval is. For example, here, if you say about on this particular number, yeah, like it's quite easy to imagine that it would end not with 6, 7, but with 6, 8. And this makes it easy to make a mistake, even though like maybe this mistake is not so important, because besides the last digit, everything was quite alright. So it fits into this confidence interval. All right, now let me demonstrate to you what happens if we don't have a significant coefficient. Yeah, so here we could say now that there is really a good, strong relationship between weight and mileage. So between weight of a car and how much fuel it consumes. Quite reasonable. We could try price, for example. So the same thing, regression, but we see that with the price, it's a bit weird. So we buy a more expensive car. So like the car is more expensive, and then it has to consume more fuel. Yeah, so like shouldn't more expensive car be more kind of energy efficient? Yeah, like why is it so? Why do you have negative coefficient? That's a bit puzzling. It's not intuitive at least. But what if we just think about price and weight at the same time? So it's quite easy to imagine that heavy cars are more expensive. So when we say that price affects miles per gallon negatively, maybe it's only the effect of weight, because normally expensive cars are heavy, and that's it. But once we control for weight, the effective price, now we see the effective price is gone. And how do we read the regression output now? We can always first refer to the p-value, and it already tells us how confident we can be if we reject the null hypothesis. And here we see that if we reject the null hypothesis, if we reject the hypothesis stating that the true beta is 0, we could say that we are wrong in 58% of cases. Yeah. So we're quite likely to be wrong by saying that there is some relationship between price and miles per gallon. So we say that this is not statistically significant. Yeah, so this is not a relationship that we would call statistically significant. With weight, it's there, nothing changed. Yeah, like the coefficient changed slightly, but still see it's significant at the 99% level. 99.9. So it's actually quite a solid relationship. All right, we can look at the graphic representation of these regressions. So here on the left-hand side we have price and its effect on MPG. On the right-hand side we have MPG and weight. So we see that here the line is much kind of much flatter. So it looks more like 0. Yeah, here it's pretty steep and explains the cloud much nicer. If you want to think about it a bit deeper, we would see that standard error, for example, of the price coefficient is larger than the coefficient itself. Yeah, so like we've seen on the graph that we were very imprecise in this estimate. Yeah, so it was not very precisely estimated. So we are wrong. So like our standard error is larger than our coefficient itself. Yeah, so it's not very cool. It's like as if you come to the airport, put your luggage on the scale, and the error of the scale is larger than the size of your suitcase. Yeah, this is not very helpful. And finally, we see that the confidence interval here includes 0. Yeah, you see, like this is negative, this is positive. So with 95% confidence, 0 is part of our confidence interval. Yeah, so like the interval that includes 0 is normally kind of it's a bad sign. So we don't have anything here. All right. And now, finally, we can do, I can analyze the coefficients we have, basically what practical meaning it has. So we'll just summarize to see it again. Weight, MPG, just to see if the coefficient is meaningful. You remember we said that like sometimes coefficients are statistically significant, but not very practically important. Yeah, so like this is a very small number. So should I care about it when I buy my car? Or maybe I can just pay, like 10 cents more per month. So like I'll definitely pay 10 cents more per month. I know this from statistics, but maybe 10 cents is like something I can easily afford. Or maybe it's way more than 10 cents. So I have to be sure I can calculate. And then you can just take the coefficient and multiply it it's the wrong number. The coefficient and multiply it with, for example, let's say standard deviation. So standard deviation shows us here like a very realistic deviation of the car weight. So an average car weighs 3,000 pounds. Yep, more or less, plus minus 777 pounds. The minimum car, 1,700. The maximum weight of the car is 4,800. For example, it doesn't make sense to me to say like, all right, I want to buy a car which is 4,000 pounds lighter than something else. Yeah, it's not a feasible number. You cannot take a car which is 4,000 pounds lighter because there is no such spread in the data. Yeah, cars cannot be that light. Yeah, so the car has to be of a particular weight. Yeah, like because you have to fit engine, you have to put the wheels and so on. Let's say I just want to have a car which is 1 standard deviation lighter than the mean. So I'm just looking at the mean. And that tells you that if you take a car which is 777 pounds lighter than an average car, for example, you just care about the average car, you will have to, or let's say it will be easier if we start with heavier car. If we know that if we increase the weight of a car, of some random average car, by that amount, we see that the mileage decreases by 4.5. Yeah, and this is roughly 25% of the mean. So basically, if we increase the weight of the car by 1 standard deviation, our distance can cover with 1 gallon of fuel, decreases by 4.5 or 25% of the mean. And now we see this is quite a substantial thing. Yeah, so like we just take a slightly heavier car. If we buy a slightly heavier car, we'll have to spend at least like on average 25% more on fuel. And this is probably something that we care about. You see, like this is not the purely thing that economists occupy themselves with. However, this is something that is very practical. Yeah, like this is a practical thing. And we can see that in this case, the effect is not only statistically significant, but it's also like substantial and meaningful. So we shouldn't ignore it. Yeah, like we shouldn't ignore it if you want to buy a car and like not spend too much time on exploiting this. All right, this is it about regression outputs. Now I show you the last thing, which is it's a paper, it's a published paper. So I want to show you how regression tables look like in journals. Yeah, because you will have to read I'll give you sometimes the papers from journals to read. So here we can read the table because you see like not everything should be included in the table. Yeah, so for example, if we know coefficient and then we know the standard error, we can estimate t-statistics, we can estimate confidence intervals, we can even do p-values, even though for p-values we need a special table. We need a special table, so maybe it's kind of not nice to the reader if we force this person not only to read your paper, but also statistical tables. So that's why some things are omitted here. And normally you read the table from the bottom, because at the bottom you can see what's inside the table. And you see that standard errors in parentheses. So these are standard errors. These are coefficients. And we also have, you see, like we have some stars. They denote these p-values. Yeah, so like 1 star is statistically significant at the 90% level. 2 stars, 95. 3 stars is 99. And here, it's quite standard regression table. You see that for every column here is a separate regression. Yeah, so this is regression which includes water and share of population in primate as explanatory variables, and dependent variable is M. Here it's, if you want to know the background story, it's the migration to the largest city of the country as a function of we are primarily interested in water access. Yeah, in some countries, water is scarce. You cannot just open the tap and drink water, or like at least take a shower. No, so in some countries, water, you have to find water somewhere. And you see that like if more people have access to water, then migration to the capital is lower. Yeah, we see this is negative coefficient. It's not super significant. It's significant at 1%, or sorry, at 90% level, sometimes at 95, but not more. So this is regression 1. This is regression 2. See, they have different combinations of explanatory variables. In the regression 6, for example, we have all of them at the same time. There at the bottom, you can see that this is the number of observations, number of countries included in dataset, and the R-squared. Yeah, so, and from reading this table, for example, you would say that, all right, we see negative, statistically, not strongly significant, but still statistically significant relationship between water, access to water, and migration to the primate city. For example, if the share of population living in primate city is high, it intensifies migration further. Yeah, and here you see it's strong. significant coefficient. Yeah, we see that this is, like, for example, this coefficient is like 8 times bigger than the standard error. Yeah, it's strongly significant. Here, it's a bit less than 2 times larger than the standard error. Maybe it's not as strongly significant, even though it's significant. Yeah, well, with cases, if you look, for example, I don't know, population density in the second column, you will see that the coefficient is smaller than the standard error. Yeah, so this is exactly, yeah, that's a 0. All right. This is it from my side. So if you have any questions, feel free. If not, then yeah, then it was everything I wanted to say. Thank you for being here, and see you next week. Yes, look, I think we have no lecture next week. We have it in a week after. But I see there's a question coming.